Yeah, or I don't know, maybe 2,000, whatever. However accurate it is. Just you keep taking. Exactly, right. Right. You good against that.
All right, so let's get started. Welcome back to day 8. We're going to be talking about residuals. So it turns out it's very timely that Alan asked a question, how do I know if my line or curve is best? I won't go over into the details of how to distinguish between different kinds of curves, but we can use residuals to take a look at why or whether or not a line is a good fit to our data. Okay? So a residual is just another name for error. And or like 5 minutes ago, we had this thing where we were like, okay, we can define the error as the point minus our predicted value. We can find a line that minimizes the errors, and the way we calculate the error is square all the errors, mean them, and take the square root. This results in the mean squared error, the root mean squared error. Residuals is just another name for that error. So this right here, another name for the error is called a residual. A residual is kind of like the more traditional stats term for it. So it's another name for the error. For every point x and y, we look at the observed y minus the regression estimate of y, which means if you have a point and a line, it's just a distance between the point and the line. That's all it is. We've already seen that before. So another way of looking at this is my observed y minus the height of my regression line at x, or the vertical difference between the point and the line. So pretty familiar. It turns out that if you look at just the error and not like look at the mean or any of all that, then we can get some interesting information. Let's take a look. All right, so here we go. Full screen. So here I have all the functions that I just defined, so I don't have to write them again. Here's little woman, here's shot put data. And what I can do is take the little woman line. So here's the regression line. We know that the residuals are the lengths of these distances right here, right? So how far away the point is from the line, that right there is that particular residual. If I look at all the distances from all the points, I get all the residuals. Okay, so what I'm going to do here is calculate the residuals. All I've done here is take my y value, take my regression line, and subtract out each point. The sum of my residuals is a -3 to the -11th power. That's like 0. So this is 0. And in fact, it turns out that if you fit the regression line to a bunch of points, the sum of the residuals is always going to be 0, which means that there's about as many points above the line as there are below the line, or distances roughly cancel out. The sum of those residuals is 0. So what we want to do instead is, if you look at the residual squared and take the average and square root the whole thing, we get back the root mean squared error. So 2 names for the same thing, error, residuals, the same deal. But what we can do is we can take those residuals. So here I have, if you look at this point right here, I have some distance, right? Maybe the distance is, it looks like 10,000, 5,000, 5,000. This one right here is really close, right? So maybe this one is like 0 or 100. This one right here is maybe like 2,000 away, right? So I have some distances. Every single point has some distance from the line. And what I can do is, instead of just drawing the points, I can just draw how far away each point is from the line. So if you just imagine with me, if I take that graph here and just rotate like 45 degrees, about, so that I can see how far away each point is from my line. That's what we call the residual plot. So I have that down here. It's a little bit hard to see, but at this 0 is kind of like my fitted line, right? So if I took the points here and rotated it, now it's not exactly the same. It's not exactly the same as rotating it, but it's roughly equivalent. It should hopefully give you like a visual idea of what's happening here. I'm roughly speaking taking that whole plot and rotating it so my best fit line is on the x-axis. Okay. If I rotate that, then I should get something that looks kind of like this, where 0 was my original line. Every point has some distance above or some distance below. Here is my residual plot. Okay, and it turns out that when the points follow like have a linear relationship, roughly speaking, the residual plot will look like just a random scatter of points. So here we notice no particular shape or pattern here. It looks like there's roughly the same amount of points above 0 as there were below 0. So we can see here that from this residual plot, the linear model seems to be like a good fit for my data. So here we go, run that. And this is the same function that we had before. All it does is it takes the sum of my residuals, which is about 0, looks at the root mean squared error, and also plots them. Okay, so here we have some data on Little Woman, and this is the same thing as we saw before. Wait, this is not the same. This is Little Woman. This right here is shot put data. Okay, so we saw before we had some shot put data. Our shot put data was not super linear, if you recall. So we had some people who lifted weights and also threw shot puts. And it looks like we had some slope here, but it looks like the slope changed in between these points here and these points over here. So I drew the best fit line, drew the original points. If you imagine with me like rotating the whole thing, and then we get this residual plot. So it looks like here we have, okay, here it looks kind of random, so maybe here's like a good linear fit. But here it seems like we have some kind of interesting stuff. It doesn't look super like scattered or spread out in this range right here. So we would say maybe not such a good fit for my data. Okay, so what we're going to do is, if we're trying to decide whether or not a linear model or whether your points follow a line, roughly speaking, the first thing you should do is always just plot your points. Right? We saw yesterday that there are a lot of cases where if you just find the correlation and just find the average and standard deviation and find numerical values, that you can get misleading values that look the same for really different points. If your points look roughly linear, then you can just fit your line. Okay? After that, another way of diagnosing whether your points follow a linear pattern or not is to plot your residuals. So a scatter diagram of residuals should look like an unassociated blob for linear relations. So if you plot those residuals, you should see a random pattern, more or less. Okay? If your data don't follow a line or follow a curve instead, you'll see some patterns in that residual plot. That'll give you a sign or a signal that maybe a linear fit is not the best thing to do. Okay? So let's talk some more about that. So I have some data on dugongs. Turns out that there's actually an animal called a dugong. It's not just a Pokemon, it actually is an animal. What are dugongs? They're kind of like manatees. What's a manatee? Kind of like a dugong. I think they're like the only two animals, like they're a branch of like the animal like species tree. So we have some dugongs. But anyway, we have some data on dugongs. Let's take a look. So data on dugongs. So we have here how long the dugong was alive. So here this dugong was 1 year old, and how long the thing was in meters. So these guys are really long. This one is almost like 6 feet long at 1 year old. Let's take a look at that. So here is my original data. Right, so the age, how long the dugong is. We can see here that doesn't really seem like a linear fit here, right? A linear model, because they grow really fast when they're young, right? The years of their adolescence, and then as they become adults, they kind of like stop growing. They eventually reach a height of around like 2.6 or a length of 2.6 meters. If you fit that line, you can already kind of tell it doesn't really fit those points super well. And in fact, if I look at the residual plot, so here are the residuals, not really random. It's a definite like looking curve thing here. So I would say probably not a good idea to use a line for this data. Right? Look at another example. So I have here data on US women. Okay. What we did here is on those. So look at US women and looked at how, I believe this is from the census some number of years ago. And what we did was we looked at the heights of women and took the average weight. So here's the height, here's the average weight. We know that the correlation is astonishingly high, so 0.99. We look at this plot. Okay, so it looks like the height and the weight are highly correlated. Okay, so correlation is really high. US women, height and weight. But if I look at the residuals, I get this. Okay, what could this mean, and why the correlation is so high? So I have this, which suggests something weird is going on, but I have this, which looks pretty linear, and I also have a high correlation. What do you think is going on? Talk to your neighbor about it.
Pretty much assumes that it's linear, almost. If your coefficients is R, assume that it's linear.
I'm just going to scroll up and down so you guys can see everything. Go ahead and talk. Let me keep scrolling.
Out of the residuals, it's a curve. That's what the R doesn't tell us. Maybe we should probably use like quadratic. Let's look at the residual plot. It's a U shape. It's a pattern.
All right, so any ideas? What could be going on? Kevin?
So it seems like the R value assumes that it's linear regression and wouldn't necessarily give us the information if there's like any patterns in there. And we wouldn't be able to see that unless we actually look at the residual plot.
Yeah, so Kevin is saying, okay, these points look roughly linear, but when plot the residuals, they're not. And so when we try to do a best fit line, you can see here that the best fit line looks like it goes through most of the points, but it looks like there's still some patterns here, right? There's still some patterns here the line was not able to capture. Any other reasons? What might be going on? Why is my correlation so high? Does that mean that if you're a woman with height 70 inches, you're definitely gonna have a weight of 155? Henry, what do you think? The scale of the second plot is very small compared to the first one. Indeed, so these are all really small numbers because my points are pretty close to the line. What about the problem of making predictions? What if it predicts that a woman with height 70 would almost always have a weight of 155? Kevin? Yeah, you got it. So again, this is what's called an ecological correlation. If you remember that thing from yesterday that I just happened to have like one line in my slides about, you have to be careful when you're looking at averages and not like individual points. You really can't like make any conclusions about the distributions of actual women based on this plot, because in this plot are a bunch of women and they're all averaged together by how tall they were, right? So even at height 70, you can get women who are lower than this average or higher than this average, but you won't be able to see that in this plot here. And in fact, if you just took the original data and plotted them, you might actually find enough points there that would make you think that there is a linear relationship. It looks like in the averages there isn't, or there's something else going on here, like these points here are all below the line, these points here are all above, right? But if you look at the individual points, maybe you wouldn't be able to tell. So it's a little bit hard to say exactly what's going on here, but it does seem like we can look at this and say, okay, these are averages. My correlation is really high, but it doesn't mean that I just predict the height of a woman based on average weight. Yeah.
This looks like a different data set.
So if these were individual women, and we looked at the scatter plot, will my errors look different? Is what you're asking. It's a little bit hard to tell. If we're looking at individual women here, there's like few enough points that I would say, okay, I wouldn't really know unless I got more data, whether or not this is actually like, whether this actually means anything or not. Yeah, so it's a little bit hard to tell. Maybe there will be, maybe there will be. Okay, so residuals, take a look, make sure they're random. Even if it looks like your data kind of follow a line, just plot them anyway. It's pretty easy to do. You can just call this function I define, plot residuals, and that'll do it for you. Okay. All right, let's take attendance. Lecture for a second half. Try to end a little early today as well. Now's a great time to fire some questions at me. Okay, so let's talk a little bit more about residuals. I'm going to talk to you about some properties of residuals. Okay? So it turns out that if you look at the residuals, there is some variance that happens in those residuals. There's some spread. Okay? Now, in this slide, I'm going to use variance, but you should remember that the variance is just the standard deviation squared. Okay? So these two things are pretty close to each other. I'm going to talk about the variance because it makes the equations look a little bit nicer in this case, so I'm going to talk about variance here. You should remember that the mean of my residuals is always 0. It doesn't matter what my original data looked like. If I find that regression line, not only is it the line where like I do the XY product thing, not only is it the line that minimizes the mean squared error, but it is also the line that gives me like the residuals sum to 0. Okay. So here's a little equation. This equation says the variance of my residuals divided by the variance of my original y values is equal to 1 minus r squared. Okay, what does this mean? It basically means if r is 1, so perfect correlation, there is no variance in my residuals. Why does that happen? Because if my line perfectly goes through all the points, I have no residuals. Therefore, there's no variation of my residuals. Okay. There's this equation that says the variance of my fitted values, so if my predictions, divided by the variance of my original y values is r squared. What you should remember about that one is if r is 0, so no correlation, a random cloud of points, right? And I fit some values to it, I'm going to fit a flat line. If it's just a complete random cloud, I'm going to fit a flat line, which means that my fitted values, there's no variation in my fitted values. It's all one value, so my variance is also 0. Which gives me r is 0. This is also 0. Okay. Yes, Kevin?
For fitted values, do you mean like the predicted values?
Yeah, so predicted values. I'm going to show you a little demo in a second that should hopefully illustrate this. So I'm going to go through this slide, show you the demo, and then take some more questions about this. This gets a little bit confusing, but you should remember like just if R is 1, if R is 0, you should remember those like edge cases there because that will help you like figure out what's going on. Okay. Finally, the variance of y, my original values, is equal to the variance of my fitted values plus the variance of my residuals. What does that mean? It means that I have some original points, they have some spread. The spread of my original points is equal to, if I fit a line, look at the spread of my line plus the spread of the residuals around that line. Let me show you how that works. All right, so I have here a little demo. See if this will work. All right, so indeed, if R is 0, oh, these points look really menacing. Let's see if I can change the color. Maybe gray. Okay, a little bit nicer. Okay, so I have here some points. I like this blue. What about Dodger blue? Let's try that. Somewhat nicer. Okay, so here I have some points. R is 0. Okay, R is 0, which means that there's no correlation. So the variance of my residuals divided by the variance of y. So basically what this is saying, okay, so let's interpret this. This one's easiest to interpret. This is saying the variance of my fitted values, the blue points, is 0. Which makes sense because all my values here are 0, so there's no variance, no variation around 0. The variation of my original points y is 1, and it turns out that if I add the variance of my fitted values and my variance of my residual values, this is my third equation, I get back the original variation. So I'm going to change the values of r. Let's watch what happens to the numbers. So let's go up. What do you notice? I'm going up, going up, going up, going up. You see here that these two numbers are changing, right? These numbers are changing, and they always sum to 1. Always sum to 1. The reason why they sum to 1 is because what I'm saying here is I'm saying how much of my original variance is accounted for in the variance of my residuals and how much of my original variance is accounted for in the variance of my fitted values. So let's take a value of r, let's say 0.5. Okay, 0.5. So it turns out that I've constructed this plot in a way that the variance of y. So the variance of y is just looking at all these gray points, looking at all their y values, looking at the variance. The variance of y happens to be 1 in all these plots. I could have made it 2, I could have made it 4. What this is saying is 3/4 of that variance is from my residuals, which means that if I look at these fitted values, look at the residual plots, 3/4 of my original variance comes from my residuals, and about 1/4 of my variance comes from these blue dots. So the variance of my fitted values, which is the blue dots, how far they spread apart, plus the variance of my residuals, how much each dot deviates from my fitted values, is equal to the original spread of my data. So it's a little bit hard to wrap your mind around this, but you can imagine it as my spread comes from 2 places, right? Take my original points. My spread can roughly come from 2 places. My spread comes 1 just because the line itself has some spread, and 2 because around this line each point has some spread. So those 2 spreads add together gives me back the original spread of my points. I'm going to amp it up to 1. What do we notice here? All the points on my fitted line, right? So there's some gray points here, you just can't see them. What does that mean? It means that my residuals have no variance in my residuals. My fitted values account for all my variance. Okay, so all the variance in y is because of these blue dots, not because of the variance in my residuals. Go back down to 0. No variance in blue, so no variance in my fitted values. All my variance is from my actual points, so all my variance is from my actual points. Go down to -1, we get the same story. Okay, so take a look at the slide here. You don't really have to remember okay, residuals, variance, all that stuff. What you should remember is if r is 1, if r is 0, what can I expect about the variance of my residuals? What can I expect about the variance of my fitted values? And try to look at the scatter plot here and play around with this yourself to get some sense about, okay, what is going on here? Any questions about this? Any values of r you want me to try? I can just go through all of them. Okay, coming flat, coming flat. More variance in my fitted value. So as I increase R, fitted values have more variance. Residuals account for less variance. Alan?
Yeah, can you go over the meaning of the definition of variance?
Yeah, so the definition of variance is not super important. It's like the standard deviation squared. What we can think of it is just the spread. So in this case, let's just think about it in terms of spread. So I'm saying, okay, the spread of all these points here, or all my original points, is equal to the spread of these blue points plus the spread of these gray points around the blue line. So you should think of variance in this case as just kind of looking at the spread of my data. Here my data are spread out, right? So here the gray points are behind the blue points. The data are spread out, but all of that spread comes from just the line. None of it comes from like that little variation around the line. Here we have most of my spread comes from this blue line, because my blue line goes up pretty sharply, but I get some spread around the blue line because these points are not exactly on the blue line. Kevin?
So basically, as R increases, do the fitted values begin to account for more of the variance as just said? Is that true?
That's right. So we can think of this as we have a spread from two places. We have a spread from the actual blue dots and the spread from the gray dots. Okay, and the spread of my original values comes from those two places, and we can, depending on the value of R, more spread comes from the blue or more spread comes from the variation around the blue. Okay, so let me ask you a question. All right, so if I look at the standard deviation of my fitted values, okay, if you remember, the standard deviation is the square root of the variance. How do my standard deviation of these values relate to R? Which of these equations is true? Talk it over with your neighbor.
Yeah, I just think roots. What? Yeah.
Okay, how many guys think, let's go backwards, D is true? Raise your hands. No takers. What about C? Some love for C. What about B? Some love for B. All right, what about A? Okay, so let's take a look at this. So SD of fitted over SD of Y. Looks like most of you thought B, but let's take a look back at these two equations over here. We have here variance of residuals over variance of Y, variance of fitted values, variance of Y. If I convert these to standard deviations, I'm going to square root both sides because these two are variances. So if I square root, I get by standard deviations. So this means that the SD of residuals over the SD of Y is a square root of 1 over R squared. If, on the other hand, I look at this one over here, square root both sides, I get SD of fitted values over SD of Y, square root this R squared, it becomes the absolute value of R, if you recall. So that means that B is true indeed. Okay, so you should remember these equations, but more importantly, you should remember what these equations are saying. Okay, so if R is 1, there's no variance in residuals. If R is 0, there's no variance in fitted values. Those are more important to me than just memorizing the equations themselves and being able to plug and chug. Okay, so make sure you understand what these are saying. And after that, stuff like this you can interpret. What is interpretation of this? This is saying, if I look at the standard deviations and use that as a measure of my spread, my correlation coefficient, the absolute value of my correlation coefficient tells me how much of my spread is from my fitted values. Similar to this one over here. All right, so let's talk about a model for regression. The last topic for today. When we're doing linear regression, and the reason why I explained all that variance stuff before, which is kind of confusing, the reason why I explain all that stuff today is because we're going to move on to doing some inference using regression. And the way we have to do inference is we first have to have a model for how regression works, or why we can actually draw that line, why it makes sense to draw a line in the first place. The model we have for regression is if we have some original population of points. Those original population of points, when we sample from the population, let's say that there's actually a linear relationship in the population, right? So in reality, there is a real linear relationship between some two variables. Let's say height of the parent and height of the child. There is a real linear relationship there, we think. And when we take samples from the population, what we get is that line, the real relationship, plus some noise. And by noise, I just mean like when we sample, there's some error in our sampling. Maybe we messed up our ruler. Maybe there's like, maybe we measure at different times of day because it turns out that you get taller or shorter depending on what time of day it is. Like you wake up in the morning, you're actually like a couple inches taller than you are at night, I believe. So we take a look and we sample. When we sample, we get back that original like actual relationship plus some noise. So signal plus noise. Here's my signal, the real linear relationship, plus my noise. So my points are now perfectly on the line when I sample. There's some deviation. And what we believe that to be, so what we do is we say, okay, if that were the case, then we think that the points come from the line, and what we do is they're probably off the line with a normal distribution. So this distance here follows a normal distribution, which means that we think most of my points should be close to the line and less points are really far away from the line if the model actually had a real linear relationship. Which means that if this is the real population, what we get to see is this. Okay, so population, here's a real underlying thing. Here's what we get to see. We only get to see these 4 points. We have to draw a line. Will a line be good? Will a line be bad? How do we decide? I won't answer that today. It'll be a topic for next week. But I'm going to show you our model. Okay. Let me turn off attendance. Any objections? All right. Close it. So draw that. So here we go. We have here the true line. And we took a sample of 10 points from that line, and we got these points. Okay. So that means that when we take away that real underlying line, we get these points. And when we try to do a regression on that line, we get this regression line. This regression line has a slope that's a lot higher than our original line. So will a regression line give us some good estimates? That's the question we're trying to ask. Okay. The question we're trying to ask is this. How many points do I need? Let's try 100 points. So here's a real line. Here's some points around it. It looks like this regression line is a little bit closer to a true line. In fact, a lot closer. If we do more points, we get here, and we get that. And we notice that these two lines are basically on top of each other, right? And what we're noticing here is that when we have a sample of points, we take the correlation. The correlation is a statistic of my data, right? Given some data, I can compute the correlation just like how I can compute the mean of some values or the variance of some values. I can compute the correlation. I can compute the slope. And then I can ask the question, how does my slope vary? Is my slope close to the population slope? Those questions just sound familiar because we've answered them before in other cases with the mean or with the median. And we can answer them for the regression case as well. But we won't do that today. We'll do that next week. I'll see you next week.